Okay, hello everyone. Today we will learn linear models and estimation by least square, part 7, and which would be the last class for chapter 11. Okay, let's move on to second example of section 11.9, which is some practical examples. In many real-world situations, the most appropriate deterministic component of a model is not linear. So far we learned linear model, but in reality, many of the situations can be explained in nonlinear way. For example, probably we can model a certain situation this way. Expected value of yt is equal to alpha 0 times e to the alpha 1 times t. Let's say we want to model the real world situation like this, then how can we use the linear model for this situation? Actually, we can do it. We can represent the same representation by taking natural log ln. So if we re-represent this equation like this, if we take ln, then ln yt is equal to ln alpha 0 plus alpha 1 times t plus epsilon. So we can model the previous situation using linear model like this. From here, we can set ln alpha 0 equals beta 0, and we can set alpha 1 as beta 1. And also we can set out this t as x. Then this is exactly the same thing that we learned in linear model chapter. Okay, let's move on to example 11.11. In the dataset of table 11.5, W denotes the weight in pounds and L the length in inches for 15 alligators captured in Central Florida. Because L is easier to observe than W for alligators in their natural habitat, we want to construct a model relating weight to length. Such a model can then be used to predict the weight of alligators of specified length. Fit the model something like this. To the data, find a 90% prediction interval for W if ln L is observed to be 4.00. Okay, so in the problem, the first one to answer is fit the model. We want to find beta 0 hat and beta 1 hat, and so as a result we want to find the model for W. And the second question is to find 90% prediction interval at the point 4.00. Okay, let's try this one first. And actually, to prove this thing, this time I tried to prove it using matrix form. So let's define our matrix X as we can define our matrix X as there are ones and 15 number of ones, and the second column represents X, which is ln L. So this is 3.87 and 3.78. This is our matrix X, and we can find beta hat using the formula. Beta hat is X transpose X inverse X transpose Y. So this is the setup from the R. Now from R, we specify our matrix X like this, and we set Y. Our Y is also a vector containing these quantities, 4.87 to 4.25. This is our vector Y, and we can calculate beta hat using this equation. And as a result, our beta hat is which is very small, minus 8.4748 and 3.43. 3.43. Okay, so now we found beta 0 hat and beta 1 hat, and so from here we can construct, we can calculate alpha 0 and alpha 1, and here beta 0 is ln alpha 0, so alpha 0 is e to the beta 0. And so here we calculated alpha 0, which is 0.0002. And so from here we can model the situation like this. W equals alpha 0 times e to the alpha 1 times L. Let's check. So this is L to the alpha 1, alpha 0. Okay, so L to the alpha 1. And here alpha 0 is 0.0002 and L to the alpha 1 is same as beta 1. Alpha 1 is beta 1 hat, so L to the beta 1 hat is 3.43. So this is our equation. W equals 0. This thing is our equation. And let's check the next question. Find a 90% prediction interval for W if ln L is observed to be 4.0. Okay, so we want to construct the prediction interval, and actually we have the formula for this. And here, to construct a prediction interval, then we should put our A as 1 and 4. 1 and 4. Which then and L equals 4, which is x equals 4. So we will put our A vector as 1, 4. Then it is beta 0 plus 4 beta 1. This is our A transpose beta hat. Yeah, and this is the confidential bound. So we can calculate this using the formula. So s square, this part s can be calculated, s square, this is s square, calculated like this, and the variance of beta hat, which is x transpose x inverse, this part is calculated like this, and here we put x star as 4, which we observe the ln L is observed at 4. This is this part, and we make our A as 1, 4, and the confidential bound can be written as this. So it is 90% prediction interval, so it is 0.1 divided by 2, which is 0.05, and this is degrees of freedom, and square root of s squared, which is s, and this part is this part. And so after constructing this formula using R, the next thing you can do is to calculate. So after the calculation, A transpose beta hat is 5.24, and the result would be 5.016 to 5.480. 5.480. So this is the confidential bound prediction interval for W when LNL is observed to be 4.00. Okay. Homework for chapter 11.9 is 11.63. Okay, let's move on to chapter 11.13, which is a test for the H0. Some part of beta parameters are 0 or not. So in this case, we have two models, a complete model and reduced model, and we are considering multiple linear regression case. And let's say our complete model, we can specify the model with k number of parameters, k number of x. So to model y, we have x1 to xk. We have k number of independent variables, and we have g, the smaller than k, g number of independent variable, which is reduced model. So x1 to xg are included in the whole xk number of whole k number of parameters. So in that sense, the model R is reduced model. So for example, if we have 4 independent variable, so if we have y equals beta 0 plus beta 1 x1 plus beta 2 x2, then let's say this is whole model, and then an example of the reduced model can be written as y equals beta 0 plus beta 1 x1. And so this is an example of reduced model. So this is whole model, complete model, and this is reduced model. And we want to test whether beta 2, we want to test whether complete model is good or reduced model is good. And so the test for that situation is this thing, H0, beta 2 equals 0. So what this is testing is whether this complete model is good or whether the reduced model is better. So if beta 2 is 0, if we reject the null hypothesis, then we probably think that the complete model would be better. And if we cannot reject the null hypothesis, then we would we would conclude that the reduced model would be better. And to do this type of testing, we use the knowledge like this. Sum of square error of the reduced model can be written as sum of square error of the complete model plus actually reduced model complete. Let's see. SSR SSC plus. Okay, right. Yeah. So SSE sum of square error reduced can be represented as this thing. And actually, the proof for this one is omitted from the book. However, I'd like to give you the intuition why this is true. And actually, if you are familiar with linear algebra, then probably you would have very good understanding about the situation. So let's say this is our n-dimensional space. This is n-dimensional space. And let's say let's say our n-dimensional space can be represented as xyz plane, and let's say this subspace xy plane, let's say the subspace 1, which is xy plane, is a space spanned by vector 1 x1 dot 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 xg plus 1 dot 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 xk. So the subspace 1 is the space spanned by this vector, and let's say subspace 2 is spanned by reduced for reduced model x1 dot 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 xg. So subspace 2 is x-axis. Okay, so subspace 2 is inside of subspace 1. So this whole dimension is the whole space with n-dimensional whole space. Subspace 1 is k plus 1 dimensional space, and subspace 2 is g plus 1 dimensional space. Okay, and in here, let's say this is the vector y, which is n-dimensional vector, y1 to yn, so this is n-dimensional vector, and let's do projection this to xy plane. We will have y hat complete, y hat c, which is if you project your vector y to the xy plane, which is y hat c, which is the projected, which is if you fitted your linear model using x1 to xk, that's y hat c. So this is xc beta hat c, which is xc transpose xc inverse xc transpose y, and here this is projection to xc, and let's say if you project your vector y to x-axis, which is y hat r reduced space, then y hat r, this is x r beta hat r, which is xr transpose xr inverse xr transpose y. Okay, so this is a projection matrix to the reduced space. Okay, and also since this is perpendicular to this, if you check this triangular, then this triangular is something like this. This part is here, this part is here, and this part is here. And so, and also the length of this part can be represented as SSEC. So this part is SSEC, and this part is SSER reduced, and this part, this rectangular part, is SSER minus SSEC. I don't have much space here, so anyway, with this triangle, you can derive the relationship of this thing. Okay, so from this n-dimensional space with this vector relationships, you can actually derive why this relationship is true. And actually, if you understand the linear algebra knowledge very well, then probably we would know this makes sense. And actually, this is geometrical interpretation and why this formula makes sense. Okay. So from previously, we derived that this SSER, the reduced sum of square error, can be divided as SSEC, and this part is SSER minus SSER minus SSEC. And so, and actually, this is like this notation: yi minus y hat r ri square is equal to sum of yi minus y hat ci completed plus y completed space I minus y hat reduced space I. Yeah, so this is this derivation, and here this is SSER and this is SSEC, and actually we can show that we can show this thing, and each of them for this chi-square distribution, the degrees of freedom is df is n minus g, and for this degrees of freedom is n minus k, and for this one the degrees of freedom is n minus g minus 1 and minus k minus 1, and for this one degrees of freedom is k minus g. Okay. And we can also show that the chi-square distribution of which is R, this one, and C, this one and this one. These two, they are independent, and so from this knowledge we can derive the F statistic this way, and here the larger value of SSER minus SSEC, if this value is large enough, then it would be the good evidence to reject that G1 to beta K equals 0. So if this part is larger and larger, that means it is evidence of the complete model would be better. So so our test F statistic can be constructed this way, and this one follows F distribution with degrees of freedom k minus g and n minus k minus 1. Okay, and I will skip the mathematical detail of how this term is derived, but if you are really interested in this, then probably you can learn this from the graduate course, or maybe it may be covered in linear model course in graduate course. Okay. Let's move on to example 11.18. Do the data of example 11.13 provide sufficient evidence to indicate that the second order model of this thing contributes information for the prediction of y? That is, test the hypothesis h0 equals beta 1 equals beta 2 equals 0 against the alternative hypothesis H alternative. At least one of the parameter beta 1 and beta 2 differs from 0. Use alpha equals 0.05, give bounds for the attained significance level. Okay, so from here, the first thing is describe the hypothesis, which we already have. Beta 1 equals beta 2 equals 0. And so this is actually reduced model. So this H0 implies that y is beta 0 plus epsilon. In the null hypothesis, our model is this, and in the alternative hypothesis, beta 1 and at least one of beta not so alternative hypothesis is not beta 1 equal to beta 2 equal to 0. This is our alternative, and which is the full model y equals beta 0 plus beta 1 x1, and actually this is beta 1x plus beta 2x squared. Okay, and so this is exactly the situation that we learned in the previous slide. So let's apply the f-test statistic in this problem. So our test statistic related to this hypothesis is this thing: f equals SSER minus SSEC divided by k minus g. K is number of parameters for the complete model, and g is number of parameter from the reduced model. And so the k is, we have 2, x and x squared. K is 2, g is 0, and SSEC divided by n minus k minus 1. Okay, this is our test statistic f, and if our decision rule is f is greater than f, alpha is 0.05, and degrees of freedom is 2, and n is here 5. 5 minus 2 minus 1 is 2. Is it right? Okay. Yeah, so this is decision rule. The next thing is to calculate. You can calculate it using R. So using R, we define our matrix X like this. X is 1, 1, 1, 1, 1, and minus 2, minus 1, 0, 1, 2, and x squared is 4, 1, 0, 1, 4. So this is our matrix X, and we can calculate beta hat this way. So beta hat is x transpose x inverse x transpose y, and also you can calculate SSE complete this way, and also you can move on to calculate beta hat reduced. So this is beta hat complete, and you can calculate beta hat reduced like this, and also you can calculate SSE reduced, and this is SSE complete. And as you after you calculate all the related values, you can calculate F statistic. So this F statistic is this thing, and you can see that this is SSR minus SSC divided by K minus G, and also divided by SSC divided by N minus K minus 1. And so the result is 12.125. So our calculated F is 12.125. And we can derive the quantity for alpha 0.05 and for alpha 0.05, the quantity is 19, and actually 19 is greater than 12.125. So our conclusion is do not reject the null hypothesis. So we do not reject the null hypothesis. And what would be the exact p-value? And here in the problem, it says give bounds for the attained significance level. And from the textbook, in textbook you only have tables. In the appendix, you have table for F distribution. But since we have R software, you can easily calculate the exact p-value. So in the problem, it always says like this: give bound. But probably in the example, I would say attain the significance level, which is calculating p-value. So you can just calculate p-value using R commands like this. This is, so here's your probably, I'm not sure how F distribution looks like. Let's say this is our F distribution. Then using PF, you can calculate the area like this. But the p-value is area here. So 1 minus pf of this thing would be area of this thing, which is p-value. So our p-value in this case is 0.0779, and which is larger than 0.05. And so that's why we cannot reject the null hypothesis. Okay. Consider the situation like this, whether we are testing all the betas are 0. And in this case, SSER is equal to SYY. Why is this true? In previously, we know this thing, SSER can be represented as SSEC plus SSER minus SSEC. And actually, this one is sum of square error R is actually yi minus yi hat. This is for the reduced space. So y hat Ri. Y hat Ri square. This is sum of yi minus y complete I square and plus sum of yi hat complete I minus y hat in reduced space I square. And here the projection to the reduced space y in the reduced space we only have one. So in reduced space there's only beta 0, which means there's only in the So we have n-dimensional space, the complete space, which is spanned by 1 to 1 x1 to xk, and in the x space it is spanned by 1, spanned by 1. And so if we project our y to the space spanned by 1, and actually this is y bar. So if you project your y to the space that is spanned by 1, that is 1 transpose 1 inverse 1 transpose y, and here 1 transpose 1 inverse, which is over n. 1 transpose 1, it is n, n inverse, so it is 1 transpose y over n, and 1 transpose y, which is sum of yi. So 1 transpose y, this is sum of yi, and over n. And so this is y bar, and here this is y bar, and 1 times y bar, 1 times y bar. This y bar is constant, and this 1 is one vector, n number of ones. So this is y bar vector, n number of y bars. So this is this one, y r hat, and so in this case y r hat is y bar, and in this case sum of yi minus y bar squared, this is syy. So if all the betas are 0, that means SSER is same as SYY. And so our F can be calculated like this. And we can show that R square, previously we know that R square can be represented like this. And if using these two formula, you can conclude that our F statistic can be represented like this. This is exercise problem 11.84a. So the one who is interested, probably you can try. I will leave it to you, so probably you can do practice. And that would not be very difficult. Okay, let's move on to example problem 11.19. It is desired to relate abrasion resistance of rubber, which is y variable, to the amount of silica filter x1 dash and the amount of coupling agent, which is x2 dash. Fine particle silica fibers are added to rubber to increase strength and resistance to abrasion. The coupling agent chemically bond the filler to the rubber polymer chains and thus increase the efficiency of the filler. The unit of measurement for x1 dash and x2 dash is parts per 100 parts of rubber, which is denoted PHR. And actually this description is a bit complicated, but the main point is we do the data transformation something like this for x1 and x2 variable, and x1 and x2 variables are listed here, and here the y is abrasion resistance of rubber, which is y variable, and how we would like to model the situation is something like here. The data are given in table 11.6. Notice that 5 levels of both x1 and x2 are used, with the x1 equals 0 and x2 equals 0. Point repeated 3 times. Yeah. Let us fit the second order model. So we are modeling, this is our complete model, and to these data. This model represents a conic surface over the x1 and x2 plane. Fit the second order model that tests the null hypothesis is whether beta 3 equals beta 4 equals beta 5 equals 0, whether this part is 0 or not. So the reduced model would be this one. Give bounds for the attained significance level and indicate the proper conclusion if we choose alpha equals 0.05. Okay, so after reading this problem, the first thing you have to do is write down the hypothesis. The null hypothesis is beta 3 to beta 5. Okay, but let's write it. This is 0 and H alternative, not beta 3 equals beta 4 equals beta 5 equals 0. This is our hypothesis, and our level alpha is 0.05, and to test this kind of situation we use F statistics. So you need to write down this formula. F is this thing, and our decision rule, you should write down the decision rule, which is F is greater than or equal to F alpha 0.05, the degrees of freedom k minus g. Here the k is 1, 2, 3, 4, 5. K is 5 and g is 1, 2. G is 2, and so k minus g is 3, and n minus k plus 1, n minus 5 minus 1. N is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 minus 6 is 5. So 3,5. So this is our decision rule. And after writing all these things, the next thing is to calculate using R. So using R, you put the data sets. You can construct a data set like this, and you can calculate beta hat, and also you can calculate SSE complete. And for the reduced space, you can calculate beta hat reduced, and this thing is beta hat complete, and this is SSE complete, and this is SSER, and this is the F test statistic that you write down here, and the result is 5.317. F is 5.317. And what would be this one? This one is 5.409, which is larger than 5.317. So we do not reject the null hypothesis. Do not reject H0. This is our conclusion, and to calculate the p-value, you can use this formula to calculate p-value. So p-value is this amount. P-value. Okay. Let's move on to exercise problem 11.85. A real estate agent computer data listed the selling price Y in thousands of dollars the living area x1, the number of floors x2, number of bathrooms x3, and the number of bathrooms x4 for newly listed condominiums. The multiple regression model of this thing was fit to the data obtained by randomly selecting 15 condos currently on the market. So we have n equals 15, and for our model we have k equals 4. And what else? If r square is this thing, is there sufficient evidence that at least one of the independent variables contributes significant information for the prediction of selling prices? Actually, in the situation A, what we want to test is whether all the parameters are 0. Beta 1 equals beta 2 equals beta 3 equals beta 4 equals 0. Versus the alternative hypothesis is at least one of independent variables is not 0, which is not H0. Okay, and the significance level alpha, where is alpha? Actually, alpha is not listed here. Okay, so let's move on. What would be the test statistic? We should write down the test statistic, and actually we know the R square, and actually what we are testing is all the parameters are 0 or not. In this case, we learned previously that our F statistic can be written as this. So this is the test statistic this time, and for the test we want to check whether our F is large enough. The related distribution for this is F, and we don't have significance level here, but we can calculate the p-value, so let's ignore for now. Let's just check that what's the degrees of freedom of this thing. Here k is 4 and g is 0. Here k is 4 and n minus k minus 1, which is 15 minus 5 is 10. So the degrees of freedom for this F distribution, this follows F 4,10. So 4,10. And from here we can calculate p-value, and so let's try to do that. So this is the calculation. R square is 0.942 as from here, and our n is 15, k is 4, and g is 0, and we can calculate our F statistic this way, which is 40.60. So our F is 40.60, and actually, if we have significance level alpha, let's say our alpha level is 0.05, then if this is 0.05, then this one is 3.478, and this one is very large, so we reject the null hypothesis. And we can calculate the p-value like this. So, and we can check that this is very significant. So we can check that our p-value, this is very small. It's very small. Or you can write down this number, e to the minus 0.6. So this is very small. And also, let's move on to part B. If SYY is equal to this value, what is SSE? And we know R square can be written as this. So if here we know R square and we know SYY, so we can calculate SSE C. So from this formula, we can calculate SSE of the complete model, which is 950. So SSE C is 950.17. Okay. Homework from supplementary exercise are these. Okay, thank you very much for your attention. This is end of the lecture on linear regression and linear model. And for the final exam, the range of the exam is chapter 10 to 11. So just focus on studying chapter 10 and chapter 11, and probably I will do some extra about probably experimental design or other stuffs. For the final exam, the range is chapter 10 and 11. So and about the exam problems, as it would be similar to a midterm exam. So all the questions would be from the lecture or homework problems, and also example problems that I explained. So study those materials, and I think everyone will get good grades if you fully understand those questions. There would be a very small modification, like change of numbers. So study chapter 10 and 11, and yeah, thank you, and see you on Thursday.